Sections 5.6 and 5.7, Finding Rational Zeros and the Fundamental Theorem of Algebra. So the rational zero theorem states that if a function f of x has integer coefficients, then every rational zero has the following form: the factors of the constant over the factors of the leading coefficient. Make sure you're aware that we're talking about integer coefficients, so they have to be positive or negative whole numbers. We couldn't have a 1/2 x squared and use this theorem. And then we're also talking about rational zeros. So if it's going to cross the x-axis at a rational zero, then these are the only places that it could cross. That doesn't mean that it might not have an irrational zero, and it doesn't mean that it might not have an imaginary zero. So let's see what this means. If we're going to list all the possible rational zeros of this function, then we're going to list the factors of the constant, which is 6, over the factors of the leading coefficient, which is 1. So my p over q would be the factors of 6 over the factors of 1. The factors of 6 are 1, 2, 3, and 6, over the factors of 1, which is 1. So, of course, if we take any of those factors of 6 over 1, we're just going to get those whole numbers. But you also need to realize that the positive and negative of those are factors of 6. So plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6 are going to be our possible rational zeros. In other words, if this function crosses the x-axis at a rational zero, it will not cross at 4, for example. It will not cross at 1/2, for example. These are the only possible rational places that it could cross. So the second example, again, we're speaking about rational zeros. We're going to look at our p over q, which would be our factors of 10 over our factors of 4. So our factors of 10 are 1, 2, 5, and 10, over our factors of 4, which is 1, 2, and 4. So it's plus or minus all of these. So 1 over 1, which is 1, 1 over 2, and 1 over 4. In other words, it's not going to cross at 1/3 or negative 1/3. Then we're going to look at 2. So 2 over 1, which is 2. 2 over 2, well, that's 1, so we don't have to list that one again. 2 over 4, well, that would simplify to 1/2, so we don't have to list that one again either. 5 over 1, 5 over 2, or 5/2, 5 over 4, and then 10 over 1. 10 over 2 is simply 5, so we don't have to list that. And 10 over 4 would simplify to 5/2. So these would be the rational zeros, possible rational zeros. It's not necessarily going to cross. It won't cross at all of those, but it also won't cross at 3 or 4. That's not in our list of possible rational zeros. So how does that help us? Well, in the last section, we were always given a zero and told to find the rest of the zeros, or given a factor. Now we might be given a function and told find all of the zeros. And so rather than try 3, for example, we don't need to try that, because we're going to list our possible rational zeros, our factors of 35 over our factors of 1. And our factors of 35 are 1, 5, 7, and 35, over our factors of 1, of course, is only 1. So we're going to try this out. We're going to see if 1 is a possible zero. In order for it to be a zero, of course, we need to end up with 0 in that last spot. So if we synthetically divide this, we get negative 32. So 1 is not a zero. So now let's try negative 1. If we synthetically divide this, we get negative 48. Again, that's not 0. So negative 1 is not one of our zeros. Remember, this is only a list of possible rational zeros. This makes it narrows down our choices, so we don't have to choose a number like 3. We know that 3 is not going to work, so we're not going to even try that. So now let's try 5. When we synthetically divide 5, we get 0. So now we know that 5 is one of our zeros. X does equal 5. It's going to cross the x-axis at 5. Now our depressed polynomial, because we started with an x to the third, is going to be x squared plus 0x plus 7, which we can rewrite as x squared plus 7. Set that equal to 0, because we know how to solve quadratics. We're going to bring the 7 over, so x squared equals negative 7. Taking the square root, we would get x equals plus or minus the square root of negative 7, which means there's 2 imaginary zeros. I don't necessarily care if you find those exact zeros, so at this point you can just tell me that x equals 5, and x would be 2 imaginary zeros. In the next example, so we've got this 9x to the 4th plus 3x cubed minus 30x squared plus 6x plus 12. So that's quite the function. We can narrow this down, the factors of 12 over the factors of 9. So those are all the factors of 12. Those are the factors of 9. So my possible rational zeros, 1 over 1, 1 over 3, 1 over 9, 2 over 1, 2 over 3, 2 over 9, 3 over 3, 3 over 1. 3 over 3 is 1, so we don't have to relist that. 3 over 9 would be 1/3, which we've also listed. 4 over 1, 4 over 3, and 4 over 9. 6 over 1. 6 over 3 is 2, we've already listed that. 6 over 9 is 2/3, we've already listed that. 12 over 1. 12 over 3 is 4. And 12 over 9 is 4/3. So these are our possible rational zeros. Now, this is quite the list. I want you to make sure that you list all your possible rational zeros. Then, if you have a graphing calculator, you can by all means put this function into your graphing calculator and look at the graph, and so you can narrow down your possible choices using your graphing calculator. I still expect you to prove those zeros by synthetic division. So if you were to put this into your graphing calculator, you would see that it crosses at -2. And so now I'm going to prove that synthetically. And so when I do my synthetic division, I do in fact get 0 in my last term. Since I started off with an x to the 4th, I'm now down to an x to the 3rd. I still don't know how to factor that, but I can see in my graphing calculator that it crosses at 1. So now I'm going to synthetically divide 1 into my depressed polynomial, because I'm trying to get this down to an x squared. When I synthetically divide 1 in, I see again that that's going to be a 0, because I get 0. So 1 is a 0. And now I have a quadratic, because I started with an x to the 4th, which means my first depressed polynomial would be an x to the 3rd, and now this would be an x to the 2nd. So I have 9x to the 2nd minus 6x minus 6. If I were to try to factor this, I realize it doesn't factor, so now I can use the quadratic formula, opposite b, plus or minus the square root of b squared minus 4. A times c is -54, all over 2a. When I simplify this, I'm going to get x equals 1.22 if I round my decimal. And I get x equals -0.55, again rounding my decimal to the nearest hundredth. Don't forget that I've already proven synthetically that x equals -2 and x equals 1. And so I've found my 4 zeros. Again, I can't stress enough, I want you to list the possible rational zeros, and then you need to prove using synthetic division until you get it down to a quadratic what those zeros actually are. The next example, a prism has a square base with a height that is 5 feet longer than each side of the base. The volume of the prism is 28 cubic feet. What is the height of the prism? So it's a square base, so I know that both of the sides of my base are x. Well, I don't know what they are, so I'm going to label them x. And then the height is 5 feet longer than each side of the base, so my height is going to be x plus 5. Realizing that volume equals length times width times height, I'm given my volume, 28, and I know that my length times width times height is x times x plus 5. Simplifying this, I get x cubed plus 5x squared, bringing everything over to the same side so I can solve this. So I subtract 28 from both sides. And now again, this won't factor, and I don't know how to solve a cubic. So if I list my possible zeros, the factors of 28 over the factors of 1 Those are my possible zeros. I could narrow the choices with my graphing calculator. If I don't have a graphing calculator, I'm going to have to basically do a trial and error and start with 1 and -1 and work my way until I find my first one. So with my graphing calculator, I can see that it crosses at 2, so I'm going to synthetically divide 2. Make sure that you realize that you need that placeholder for your x term. Otherwise, even though you see that it crosses at 2, if you don't have that placeholder, this wouldn't work out right. Doing my synthetic division, I get that 2 is in fact a 0 because I get a 0 as a final result. My quadratic then, since I started with an x cubed, is going to be x squared plus 7x plus 14. If I were to use the quadratic formula, I see that I get a negative inside the radical, which means there's going to be imaginary solutions. So x has to equal 2. I'm asked to find the height of the prism. The height is x plus 5. Plugging in 2, I get that the height is 7 feet. Now, we've already discussed the fundamental theorem of algebra in class. The fundamental theorem of algebra states that if a polynomial is degree n, then it's going to have at least one solution, and more importantly, it's going to have exactly n solutions, provided that you allow any repeated solutions to be counted. So in other words, what does that mean? In this first example, if I have an x to the 4th, it's a degree of 4, there's going to be 4 solutions. And the second one, the highest exponent is 3, therefore there's going to be 3 solutions. The third one, it appears as though the highest exponent is x squared, but if I were to multiply all these binomials together, x and the x squared, I'm just looking at what I would get for my highest exponent, I would get an x to the 4th, which means it has 4 solutions. So this example is just like the previous two that we've already done. I'd like you to try to do this one on your own. I will kind of zip through this one so you follow the process again. Listing my possible zeros, and then you need to make sure that you prove them. So I look at my graphing calculator and I see that -2 is where it crosses. Notice that this is an x to the 5th, but that there's not an x to the 4th term, so I need a placeholder. And there's not an x term, so I need another placeholder. Proving that -2 works, I'm going to continue with my depressed polynomial. I see that it crosses again at -1, and I prove this one. So again, -1 works. Again, with my depressed polynomial, I can see that it crosses at 2. And now, hopefully you recognize that you're down to a quadratic, because I started with an x to the 5th. My first depressed polynomial was x to the 4th. Second depressed polynomial was x to the 3rd. And my third depressed polynomial is an x to the 2nd. So I have x to the 2nd minus x plus 1. I'm just going to try the b squared minus 4ac. If I get a positive number, then I'll have to use the full quadratic formula or try to factor it, which it won't. But if I end up getting a negative number, which I do, I can simply state that there's 2 imaginary zeros. But again, I want you to prove to me by doing at least the discriminant that you're going to get 2 imaginary zeros. Please do not rely on just looking at the graph. So the fundamental theorem of algebra says I need to have 5 zeros. I've got 1, 2, 3, and 2 imaginary would make 5 zeros. The conjugate's theorem, if a plus bi is a 0, then a minus bi is a 0, and if a plus the square root of b is a 0, then a minus the square root of b is a 0. So something else you might be asked to do is to write a polynomial of least degree given the zeros. So given the zeros, that means that x equals 2, and that x equals -2 minus 5i. But the conjugate's theorem then also states that -2 plus 5i is a 0. Simply working backwards, I'm going to write these as factors, subtracting 2, adding the 2 and the 5i, adding the 2 and subtracting the 5i. I would recommend, first of all, foiling the second 2 with the i's, because you'll notice that as I multiply this together, again, foiling, multiplying everything in the first parentheses by everything in the second parentheses. And now I'm going to combine like terms before I multiply that x minus 2 times that big mess. So I have an x squared. I have a 2x and a 2x, which gives me 4x. I have a negative 5ix and a positive 5ix, so those will give me 0. I have a negative 10I and a positive 10I. Those give me 0 as well. And then I have plus 4. And then remember that I squared equals negative 1. So negative 25I squared is the same as plus 25. Well, 4 plus 25 I can rewrite as 29. And now when I multiply, I have no more i's, and it's just a matter of multiplying everything in the first parentheses by everything in the second parentheses. Combining my like terms, x cubed, 4x squared minus 2x squared is 2x squared. 29x minus 8x is 21x minus 58. Notice that there are no i's. If you multiply and do this right, there should not be any i's. No imaginary zeros. The very last example is using a graphing calculator. This is too difficult to explain without actually showing you with a graphing calculator in front of me, so please see me about this one. This was a fairly long section. I apologize. If you have any questions, please get them answered by asking.